In the first dot point for this module, we measured the temperature changes in some chemical reactions. And the temperature is changing because there's energy absorbed or released in a reaction. And what we're going to try to do now is measure the amount of energy that's absorbed or released, not just a temperature change, but how much energy in joules was absorbed or released. And we use a process called calorimetry. This is an important method because we'll use it again in year 12. And you need to learn the principles of it now. There are some confusing things about it, so we've got to understand it well. And calorimetry is a process to measure the heat absorbed or released in a reaction. What we do is we make the reaction take place in an insulated container with a known mass of water. So at the simplest level, it could just be a foam cup like this one here. We put a thermometer in so we can measure the temperature change in the water, and that does allow us to work out the energy that was absorbed or released. That's the basic principle. Capture all the heat from the reaction in the water, and the temperature change in the water allows us to work out the amount of energy that was released or absorbed. What does a calorimeter look like? On the left, you can see one that is an insulated container. Around the outside, there's insulation. In the center, you've got the vessel where the reaction will take place. It's got water that will capture the heat. You've got a stirrer to make sure the reaction is proceeding well, and you've got a thermometer so you can measure temperature change. That's a basic calorimeter. If you want to measure the energy released by a reaction that is not in solution, the one on the top right is an example of how you could do it. In the very center is a vessel where the reactants are placed. You can see them at the bottom there. Then around that is another container. So it's inside another container full of water that is going to capture the heat, and we will measure the temperature increase of that water. How do we start the reaction? Well, on this one, they've got electrical connections going down so they can set off a spark to start the reaction. But it's the same principle. Capture the heat from that reaction in water and then measure the temperature change of that water. And down the bottom, the picture is what a typical calorimeter might look like, a good commercial calorimeter. How do we do the calculations? How do we actually measure the energy absorbed or released? And this is what you'll be focusing on. Well, what are we going to need to know? Obviously, if the temperature increase is greater, more energy was released. So we need to know the temperature change, and that's final temperature minus initial temperature. Also, if it takes more energy to heat a greater mass of water, so we are going to need to use the mass of water. If you have a very large amount of water, the temperature is not going to increase much from the same reaction. So we're going to need to use the mass of water. And the last thing, we also need to know the specific heat of water, and we use the symbol C. And that's how much energy it takes to raise the temperature of 1 gram of the substance like water by 1 Kelvin. So they're the three things that are in our formula, and it's as simple as multiplying them together. So the total heat is calculated. Q is the symbol for heat. It's just mc delta T, the mass of the water that you heated times the specific heat capacity of water times the change in temperature. That's it. It's a simple formula, but it starts to get confusing in some of the situations where we use it. The formula is given to you on the data sheet, and the specific heat capacity of water is given to you on the data sheet. You'll notice it's a very confusing units for the specific heat capacity of water. It's 4.18 times 10 to the 3 joules per kilogram per Kelvin. But having that listed on the data sheet is very helpful because it tells you what units to use as you substitute things into the formula. The units must match. So when you do mass, it's got to be kilograms because that's what's in the constant. When you do temperature, it's got to be in Kelvin. And your final answer, you can see from the constant, it will be in joules. So the constant actually tells you what units to use when you do your substitution. Now, there is a trick with Kelvin. So we could convert all our temperatures from degrees Celsius to Kelvin, and we learned how to do that in Module 2. For example, 0 degrees Celsius is 273.15 Kelvin. So to convert, you just add 273.15, and that's to convert from Celsius to Kelvin. But there is a trick. The difference in temperature is the same in degrees Celsius or Kelvin. You think about it using that scale on the right. If I increase the temperature from 0 Celsius to 100 degrees Celsius, what's the change? 100 degrees Celsius. If I measured that in Kelvin, I increase from 273.15 to 373.15. What's the change? 100 Kelvin. So if you're using a temperature, you do need to convert. But if it's a change in temperature, it's exactly the same whether it's in Celsius or Kelvin. So it is okay to just calculate your change in Celsius and then say that's Kelvin. That makes it much simpler with temperature. Now in class, we did a quick investigation where we just heated some water, measured the temperature change, and then we can calculate the amount of heat that went into that water. Here's a sample of how you do the calculations. And so you can have a look through that, but it is pretty straightforward. And then here are some sample questions that you can have a go at. Do question 1, that's a straightforward one. Question 2 changes it around a little bit. That's good to have a go at. And then question 3 is a challenge question that is good if you've got time to try, but it is deliberately challenging.